No. All right, so I have a bunch of papers for you, so I apologize, I don't know what happened with chapter 6 homework. So I wasn't notified till this morning, so I have it reprinted. We're doing 2 labs this week, so I have that printed for you. Yeah, we are at the end of the quarter. I have your gas laws homework, and that should be double-sided. Double checking everything now. I'm trying to. And your labs, so energy and solutions lab. All right. Any questions before we get started?
We're doing both labs on the same day, right?
Yeah. Yeah, the energy one is pretty, like they're both pretty simple labs. Just a lot of doing, but a lot of short activities. And then next week is lab 9, and then after that is your lab practicum. So you'll have like a little final. Shouldn't be too bad though.
You just want to know if there's fire involved. Is there fire involved? That's all he cares about.
No.
Oh, come on. I felt like there was a good statistical chance because we've had a lot of fire ones, and you said it was going to be one of the ones we did already, so I was hoping.
No, I'm picking boring stuff for the final.
Okay.
But if I wanted to make it hard, I would do like the chemical identification one, making you do that on your own. It'd be more fun. I don't know if y'all would want me. I would want to do that.
I don't think I could have said this.
Please don't have a say.
All right, other questions before we get started?
So these are different packets then?
Yeah, because I misprinted 6. It was only one-sided.
Oh, okay.
So your chapter 6 homework is only half done, so you don't have to give that to me today. All right, so solid, liquid, gas. And so this is kind of a little refresher from before. So we said a solid has a fixed shape and volume. Liquid has a fixed volume, but like I'm sure you see every day, your coffee and water pours into any container. And then a gas, we use that special word of compressible. So gas can be compressed, sometimes all the way down to a liquid, like we saw with liquid nitrogen. And then once it's released, it can expand, of course, and fills the entire room. And so gas is then just a phase of matter where particles are moving randomly and very fast in their container. And so now we take, this is where we kind of give an idealized look at what a gas is. And so we have our kinetic molecular theory. And again, this is more of an ideal view. And so we're saying that gas particles move in straight lines. And that's basically true. It's just in this case, we're just ignoring any sort of interactions between molecules. We're just assuming no intermolecular forces. And so they're also going to just be elastic collisions is how we are treating them right now. So they're just colliding, or they move around until they collide with either the wall or another particle, and then again they bounce off. So again, not taking into account any energy loss, just assuming perfect elastic conditions. And basically, when your molecule collides, that's the force it exerts, and it collides over the force of a surface. So you could measure that and average that as pressure. So pressure is just force over area. And so we have pressure defined here. And so again, pressure is just force over area. So how much are those gas particles smacking down basically on your surface or your manometer, whatever you're using. to measure the gas. And so this gas pressure depends on a few factors. And so the number of gas particles is a factor, and that makes sense, right? More molecules means more of them smacking down, so more pressure. Your volume is also an influence, and that makes sense. You're dividing it over area. So if your container gets larger, then you're spreading out those force, whereas you have a small container, right, much smaller area, so that force is concentrated. And then speed, of course, is another factor, and so we'll kind of see this in terms of temperature related. So basically temperature is related to your kinetic energy, and so the faster they're moving, the more they're smacking down and colliding, and so that increases pressure. And so like I mentioned, here's the assumption that we make. So we assume perfectly elastic conditions, so no exchange of energy. And so if there is an exchange, or really in the real world, these are inelastic conditions, but again, for our purposes, we're not thinking about this, we're just treating them as perfectly elastic. And so we have several units of pressure that we can use. And so again, this is your manometer here. So we have our glass vacuum tube. So this is evacuated out. And so as these air molecules smack down on our pool of mercury, it drives some mercury into the tube. And so this is where you get the weird, crazy measurements. And so for instance, 760 millimeters of mercury, so that corresponds to a height of 760 millimeters. So that equals 1 ATM. And then if you notice, the units of millimeters of mercury and millimeters of torr are interchangeable. So 760 millimeters of mercury equals 1 ATM, which is also 1 torr. And so you have your notes and everything, but you'll often see, right, these are used pretty interchangeably. And you could also see inches. We probably won't see too many inches in our word problems. It's usually a torr to ATM conversion, but just keep that in mind, that that's where that comes from, that height converted from millimeters to inches. And so there are other units of pressure too, but again, this is more an appreciation, and you can convert if you ever need to. So PSI, this is often used in like your cars. You usually fill up your car to like 33 PSI typically. You have pascals, so 101,325 pascals is 1 ATM. So there's inches of mercury. We have bar as well, which is like used for the weather, and then ATM. Yeah, it's just atmospheres.
Oh.
So it's like 1 atmosphere is just like your usual atmosphere.
So it's like 1 atmosphere. Okay.
Yeah. So people like ATM, especially if you're like maybe talking about the sea, and then like, oh, you know, that's where you get like the doubling of the atmosphere as you go under, it starts increasing.
Okay.
And so we can kind of look at these 4 basic properties of a gas. And so a gas is going to have a pressure, and ideally your unit would be an ATM. You could convert there. We'll talk about formulas and when it's essential to convert or not. Then we usually define a volume, so volume usually given in liters, and then temperature, so we can get the temperature of the gas. That's always in Kelvin, so star Kelvin. So anytime you work with temperature, at least in these thermodynamic properties, you're going to be talking about Kelvin, and that's just so we thermodynamically make sense. So, right, the problem with Kelvin, or the problem with Celsius, I should say, is that it goes negative, right? And that's great for our purposes, but if you're trying to plug it in thermodynamic values, and you have negative numbers, it doesn't make sense. So keep it with Kelvin, so it's thermodynamically consistent. And then we'll talk about moles as well, so good old moles will come back to haunt us or to have fun with us. And so what we find with gases, and this is really important and key, is all these properties are interrelated. And so that means we can change one and it affects the others. And so we'll look at these kind of simple gas law relationships and then kind of figure out how to extrapolate that. And so this is a quick overview of the 3 simple laws we'll be looking at. So let's start with Boyle's, which is just pressure and volume, Charles's law, which is volume and temperature, and then Avogadro's, not to be confused with avocado. Avogadro's is volume and moles. But like I said, we'll look at each of these individually. And so Boyle and Hooke were experimenting with these different little J tubes, so basically little sealed tubes with different volumes of gas samples at different pressures. And so they would trap air in their little J tube and add mercury, and that would increase the pressure. And so they started noticing an inverse relationship. And so we essentially have a piston example here. So we have our volume is 1 liter. We're at 1 atmosphere of pressure, 1 kilogram mass on it. And so this is just a weighted piston. So if they put more on top, like mercury, so increasing the mass on here. So what that does is effectively shrinks the volume. And so in this case, if we have a volume of half, so 0.5 liters, notice how that doubles the pressure. And so that's our relationship, yeah.
So, this will be in the book though too, right? The chapter 7 in the book. Okay, so just want to double check. Because I understand it both ways, so I just wanted to make sure the information's on both of them.
Yeah.
I just take a lot of notes when I'm reading the book, so.
Yeah, and then also OpenStax, if you wanted to look at that book, just any gas chapter is what we're on, so just basic gas laws in chemistry. And so what we find is, again, as volume is decreased, so now they're in a smaller space, our pressure increases. And so here's a little graph now. So it states that our volume of gas is inversely proportional to pressure. And so what happens when you reach this limit? Notice how it's kind of plateauing. What do we encounter? Like what does that indicate? So max compression, would you say?
Oh, so is there no more volume available left?
Basically, so you're kind of like, I feel like you're both touching on the right point. So what happens when we're down at these extreme pressures in very small volumes? I feel like you both are like touching on it. But is there another way to phrase it? Like what's the limiting factor, I guess?
I think the limiting factor is the gas.
Yeah, so you're talking about like the physical size, right? Yeah, so I think you all were dancing around it, but that's it, right? So you use the words max compressibility, but basically, right, you're at the physical limit, and you use no more volume, but right, so at that volume are literal atoms now, right? Just we cannot compress them anymore at that limit. So that's what we see reflected there. Excellent. So now we can't compress them. And so the important part is this math relationship here. And so P1 V1 equals P2 V2 but again, we'll go over how we can derive all of them at the end. And so this is what we're talking about with diving. So for every 10 meters of depth, a diver experiences approximately 1 additional atmosphere of pressure due to the weight of the surrounding water. So at 20 meters, you would be experiencing 3 atmospheres of pressure. And so what happens with the gases, and why do you have to rise slowly? Or has anyone ever dived in or scuba dived? Yeah, so what happens?
When you climb too quick,
Yeah, and why?
well, first off, you can get really sick or die.
Yeah,
But basically what happens is you have air in your lungs, and then when you climb up, they rapidly expand, so you can actually blow out your lungs.
yeah, so that's the main part, right? And you're just thinking of that pressure-volume relationship. So same thing even in your cells, right? All the oxygen that's dissolved in your blood and everywhere. So all that, if you rise too quickly, has to go somewhere.
And most common and most worst is your blood, because your blood will actually rapidly, the oxygenation in your blood will rapidly expand. I've heard horror stories.
I have never heard the horror stories. I just hear everyone say that's why you go slowly. Maybe you can share horror stories later because I'm kind of curious out of my own morbid curiosity. But yeah, I mean, people refer to it as the bends just when you get sick, but yeah, obviously you can have severe consequences or damage internal organs like it mentions there, but you want to exhale, but again, also go slowly so that everything can acclimate. And so that's, again, chemistry why. All right, let's do a little practice problem. So as you breathe, you inhale by increasing your lung volume. So that's actually what your diaphragm muscle does, is it makes everything larger. And so you have an initial lung volume of 2.75 liters, which is filled with air at an atmospheric pressure of 1.02 atms. If she increases her lung volume to 3.25 liters without inhaling any additional air, what is the pressure in her lungs? So just imagine, right, let's say she's going to inhale, so if we could just freeze that point where that lung volume is increased, but we haven't intaken any air, what's our pressure?
Trying to find the pressure, right?
Yeah.
So would you convert it from the liters of air to the pressure, or ATM?
So we have everything in the units we need because we have liters, ATM, we're looking for ATM. And then this is our formula.
Oh, okay, there it is.
So I'll leave it there for a second. Give people more time.
Oh, those stand for pressure and volume, right?
Yeah.
Okay. So you take the pressure of one.
Yeah, so this is, you'll take your initial conditions, multiply them together, and they equal your second set of conditions.
So the standard pressure, standard volume, and then
Well, it's not necessarily standard,
not really standard,
just whatever you're starting with, right?
yeah, starting, that's what I meant, starting
Yeah.
pressure. if you could scroll back down just for a second? So
Oh,
we
yeah.
can have the other numbers.
And so, of course, the hardest part is just identifying who's your P1, your V1, your P2, your V2. And so, you may want to just start with that really explicitly. So we have our initial lung volume, and then we have our initial pressure, switch, and then our final volume. And then we know which ones to plug into our formula. And so in this case, we also didn't have to do any unit converting, and when we're just kind of comparing, it doesn't matter like what your volume is in. So if there was both in milliliters, that would be fine. If the pressure was in torr, that would be okay, as long as you're not doing like any PV equals nRT combined gas laws, and we're just invoking comparison. I don't know if I explained that well. All right, so what do we get for our new pressure?
0.86.
So 0.86 ATM. Did you have a question?
Oh, would it be, are we going with 3 sig figs or sig figs not matter here?
3 sig figs. So you could,
363. Yeah, 3.
Okay, I must have rounded, oh yeah, I rounded differently, that's why.
so yeah, little differences in rounding are fine. Excellent. Any questions about this one?
So that's the second volume then?
Or pressure?
Or,
Because it's asking for pressure. But it would have worked, right?
oh, we already have volume.
Yeah, but they could have given us, right, so they could have said, oh, what if the new pressure was 0.863 ATM? What is the volume that she increased her lung to? So it really didn't matter which one we were solving for. It's just all, we could have also been solving for P1. It's just all about what's given, as is with all these chemistry problems. All right, so looking at Charles's law, and you'll get good practice with the homework with all of this, so then you'll feel hopefully a lot better. And so with Charles's law, they said that volume and temperature have a direct relationship. And so this kind of makes sense. And this is also when you're holding, right, everything else constant. So that's also the trick with these simple gas laws. So holding everything else constant. And this means, right, that our pressure must be constant. So P1 has to equal P2. Pressure constant, since we're not talking about pressure. And so what that means, okay, so we have a fixed volume, or we have an initial volume, temperature, and then if we start increasing the temperature, right, everything's going to start moving faster. And if we need pressure to be constant, then we're going to have to increase our volume. So that's what happens. And so that gives us this relationship here. So V1 over our initial temperature is equal to our second volume over our initial temperature, our second temperature. And so this is where temperature has to be in Kelvin, because again, you don't want negative numbers down here. That'll screw up your proportion and would not be good. So always be in Kelvin. the volume, the units don't matter as much, so they could be in liters and liters, milliliters, milliliters, as long as they're the same. I was looking. See if that works. Have you guys ever played with these like FET simulators before? Some people have. I'll put this out as a link. So this is just kind of fun to play with. So it goes through the different gas laws. So we're under the ideal gas laws. So I was going to do, why won't you let me hold pressure constant? Confused. Okay, let's put some particles in there. Oh, there we go. Yes, I want to hold pressure constant and saying increase of volume. Oops, that's not what I wanted. So now I told it to hold pressure constant, so let me heat it up. So now we're at 0.6 atm. It's going to hold it constant. And so, of course, right as it's heating, notice how it's expanding the container, oops, to keep that pressure. And so going back to Charles's laws, so like we're kind of seeing with that, again, our volume of gas is directly proportional to our absolute temperature, just meaning we have to be in kelvins, we can't go negative. And again, all we're saying is we increase the temperature of our gas, like we were doing with our little simulator there. So then the speed starts increasing, and we had to expand our volume out so that our pressure was unchanged. And so now here's our graph of Charles's law. So if we could extrapolate everything back, we would always end up at our absolute 0 point. And of course, we have the issue of our gases condensing into liquids. And so we could do this too. Oh, there's a fun video, actually. I'm sure you guys have seen. Let's look at it. And so this is another explanation, and I'll pull up a video as soon as YouTube loads. And so again, our temperature, if it increases, our gas particles are moving faster, versus if we cool them, so then they have low kinetic energy, then our balloon would shrink. And so let's look at this demo that they do. Come on.
Hi everybody, I'm meteorologist Jay Burschback along with Carl Nelson at the Imagination Station. Today we're dealing with one of my specialties, air pressure, the power of air pressure. And you may have seen this experiment before using a gas can or a smaller can. This is big scale. This is the Imagination Station's version of supersizing that experiment, showing air pressure which can crush this huge barrel. Carl.
So we got a steel 55-gallon drum here. I just want to give you a sense for how strong, how rugged these barrels are. Jay, if you could stabilize the barrel, I'm going to take a sledgehammer and try to... If you relied on me to crush this barrel, we'd be here all day.
Sure.
Because that thing is pretty tough. So instead, like you said, we're going to use air pressure to crush this drum. So I'm going to flip this up. I'm just going to stick it on its end here.
On its end? Oh, okay.
Because what I'm going to do first is add some water inside. About 6 cups of water. And what the water's going to do is we're going to create water vapor inside that we're going to heat up. Now water vapor when it's warmed up and air when it's warmed up occupy a little bit more space. Our goal is to try to trap some of that expanded air and water vapor inside. We're going to seal this up and then cool it down.
Okay.
We should see some crushing action at that point. But first, we're going to need to heat that air up. So help me flip this up on
All
our
right.
stand here.
Okay.
The thing we're looking for, Jay, is we want to see a nice solid stream of steam coming out this opening here.
Sure.
And in order to do that, we can't just use like a blowtorch or anything small. As this is the supersized version, we're going to use one of these road torches.
Yeah, I think I'll back up.
Okay. So it'll take a few seconds here to get the water warmed up inside the barrel, but to give you an idea how big the flame we're going to work with.
All right, next time we're roasting
Okay, I think you can see there's a good sort of jet of steam shooting out, but we're going to try to capture that.
Okay.
By putting the plug back in. We're going to wrench it down tight because we don't want any of that warm, expanded air to escape. But the key now, Jay, is wheel over that tray of
Now,
ice.
this is
We're
important,
going to cool
right?
this baby
There's our
down really
closed
quick
system.
in a tray of ice. Hold on. I'm going to spin it around. Look into it. Now, the first thing we should hear are a couple of the ends of the drums popping in.
There we go.
A couple of the ends going in. There's the other end. There we go.
There we go.
Give it a second.
So what we're seeing is air pressure literally crush.
14.7 pounds per square inch of normal atmospheric pressure are now pushing down on this drum. And because that water vapor inside and that warm air inside
There it
has
goes.
cooled down, taking up less space, doing a lot more damage than that sledgehammer did earlier.
That is amazing. Looks like a pop can or a so.
Yeah, so that was basically Boyle's law. Just doing a little bit differently from this case, right? So instead they took their container, it was open system, right? They used water so they could condense the water back down. But they kind of, right, replaced, at least the idea was replace all the gas inside with your water molecules. They said they wanted steam coming out. So then we sealed it up with less molecules of gas inside, right? Then cooled it back down, and we could do some math probably to have figured out the crushing, and then that's how they crushed it down. So again, similar with this balloon. So if you have, it depends of course when you close the system, but if you have your closed system with our balloon and then put it over some boiling water, it should expand versus again that ice water. All right, so let's try this one, and I'll rewrite the formula above. And so we now have a sample of gas, has a volume of 2.8 liters, and now we're starting with an unknown temperature. So it looks like we're solving for T1. And we submerge our sample into ice water. Its volume decreases to 2.57 liters. So what was its initial temperature? And so it's kind of almost trying to trick you or maybe help you. So it wants its initial temperature in Kelvin and Celsius. But don't forget temp must be in Kelvin for the math to work out. We have answers.
Not sure that's right.
What do we get?
I got, 0.918.
0.918. That's,
Yeah.
that just sounds funny, because if that was Kelvin, that'd be really, really, really cold.
Well, I just wasn't sure, because, the way I set it up was, I took the V2, so the 2.80, and I, cause it's the unknown temperature, right? So wouldn't that be the second one? Wouldn't that be, not standard?
You could set it up as V2, V1. It doesn't really matter too much, but you have to get, yeah, what'd you get?
Where'd you get the 2.73 from?
273.
273. Where'd you get that from?
Temperature in Kelvin of your initial temperature.
Oh, I had no idea that, okay, that's why I messed up on.
Yeah, that's why I said temperature must be in Kelvin, and then we had to remember how to convert to Kelvin or look back in our notes. So you add, remember temperature Kelvin is this temperature Celsius plus 273. Yeah,
Got 297 degrees Kelvin.
so 297 for our initial T1. Is that what other people got?
Wait, can you just explain, I got that right there, all that. Basic geometry.
Okay, so then
How do you do that?
this is just cross multiplication. So the easiest is to do 2.8 times the 273 and then divide by 2.57.
Did you want the Celsius with it?
Yeah,
It was 24.4.
so 24.4.
Yeah.
So you cross multiply the 2.8 by 273?
Yes.
Even though the 2.8 is liters and the 273 is kelvins?
Yeah, because it all cancels out. So you have to solve it initially in Kelvin, and then you can do your Celsius conversion.
So where do you go after you times it, after you cross multiply?
So then, once you solve, because once you cross multiply, that should give you x, right? So that should give you 297. And so I could plug that in. So 2.8 times 273 divided by 2.57. Oops. So then that gives me that answer.
Oh, you need to divide it by 2.57?
Well, you have to get X by itself.
So then did you get 297 for x? So then that's your answer in Kelvin. And then minus 273 gives us our Celsius answer.
But then you need a minus, even though 273, even though you multiplied it beforehand.
Well, this is just the temperature Kelvin to Celsius conversion. That's all that little part is, right? Because in the beginning, we added 273 to the 0 to put it into Kelvin. Then we did the math. Then we can convert it back to Celsius or just leave it in Kelvin. And for this, I don't care personally what you put it in Kelvin, Celsius. If you leave it in Kelvin, that's fine. Unless, of course, the problem specifies put it in Celsius. Like I said, homework is full of practice, so we'll feel better. We'll put it all together, and it won't just be these disjointed formulas. All right, so Avogadro's law. Now, volume and moles have a direct relationship. And we can bring back our little PhET simulator for this. So let's not hold anything constant. And so we have, 6 particles in there. And it says again, if we increase moles, then our volume is gonna have to increase if we're holding everything constant. So we're holding pressure and temperature constant, so now let's go back to this. So we're gonna hold pressure constant, and this means that we're gonna change volume, so not temperature. So if I had picked that, we could change temperature to keep pressure changed, or the same, not speak today. And so we add a particles, now I'm gonna go up to 7 particles, right? And then our volume increased to keep our pressure at 0.9. So now 8 particles, we're still at 0.9, 10 particles, still at 0.9. We're just making our box bigger so that our pressure stays the same. And so that's all Avogadro's law is saying. So pretty self-explanatory, and it makes sense, right? You physically add more gas, then if you want our pressure and temperature to be the same, then we have to increase our volume. And so it gives us this relationship, and I'll just rewrite it. So volume 1 over our initial moles equals volume 2 over our final moles. And so this is all molar amounts. And so notice, right, the identity of the gas doesn't matter, especially how we treat these ideal gas law scenarios. They're all the same, we just care about the moles. And so like we looked at, our volume of gas is directly proportional to our moles. Increasing our molecules means that we need to increase our volume to keep pressure constant.
Can you go back up to this one?
So this one?
Yeah.
And then I'll just rewrite them B1 over N1, B2 over N2. And so you have a male athlete in a research study has an initial lung volume of 6.15 liters during a deep inhalation. And at this volume, it contained 0.254 moles of air. During exhalation, his volume decreased to 2.55. And so this is kind of tricky with this question. It asks how many moles of gas does the athlete exhale? And I'm just going to grab some water.
Yo, do you want me to redneck flamethrower?
What?
I would like to never hear those 2 words in that exact order ever again.
Did you do that?
Please don't ask.
What does that mean?
No.
What does that mean?
Don't ask.
I didn't want to get in trouble if I explained.
Yes, you will.
For my curiosity.
I'm still working on this one. Want your 2-for-1 bang again?
A good bang for your buck.
Nah.
Oh, God, I love the jokes.
And do all bang flavors have artificial sugar?
Artificial sugar.
I'm gonna assume yes, but I don't know.
I was trying to find, because I like going to the Dollar Tree, you know, as like a activity. And I was like checking out all the energy drinks, because I like energy drinks, but I like real sugar. I can't stand fake sugar. Like,
Yeah, so this uses sucralose. What's a good one?
it's not even a health thing. It's just like the taste is so off to me.
If you want to do taste, there's one called Ghost.
Oh, yeah,
Oh,
ghost.
I've been
Those
wanting to
taste-
try that one.
Those ones taste really good. They do have fake sugar in them, but you don't taste the fake sugar. They are probably the most accurate description of whatever they say on there. It messes you up a little bit.
Ghosts are so good, like,
There's another one. There's actually like they call it the healthy energy drink. What are they called? Celsius, something like that. They're actually made mostly from like natural stuff. There's not a lot of artificial flavoring in them. And I'm pretty sure they use all natural ingredients, including sugar.
I'll have to see, because
But-
a lot of them like using stevia, and they're like, it's all natural. I taste that stuff.
I once tasted a stevia root beer, that was god-awful.
Dude, I won't drink the stevia sodas. Although I try not to drink soda, period. If I do splurge, my favorite is when they have like the ones that are like the limited edition real cane sugar.
Oh, yeah, those are good.
So much
Yeah.
better.
I know, I always get the Costco, like, Mexican Coke, because I want the real sugar.
Oh, yeah, that sounds like way better.
Yeah.
But I don't, as I said, I don't like to drink soda, so I go to Food for Less because you can get them for cheap and like individuals. And they have like all of the Fanta, like the Mexican Fanta, Sprite, all that stuff, so they all have the real glass bottles, old school style.
Nice.
They even have those like Paritos.
Oh, yeah, those
I
are,
love those. And they're like the real style, not like the plastic bottle.
see, are we still calculating? We have answers.
I remember when Mountain Dew did a thing called Dew Shine, it was like just Mountain Dew made with real cane sugar.
See, that sounds great.
It was awesome.
I think I was like a kid when it came out.
Probably, because I was a teenager.
So let's see. So walk me through. So we had to first solve for how much he had after. So what do we get when we solve for x for this? 0.105 moles. And then we got that this was remaining, right? So then we had to do the subtraction. So how many were exhaled? 0.1, what did you say, 0.14? 0.149 moles were exhaled. So as long as you got this was, you know, a good first step, and then this, that was just a tricky part of the question is reading the exhale. But this is good. If you got there, then you can set up the formula.
What did you subtract it by?
Oh, just the initial. because it was just a tricky
Oh.
word problem. So then if we initially had 0.254, we had 0.105 remaining, so that's how many were exhaled.
So you subtracted by 0.254, okay.
Take 254, subtract 1.105.
Yeah.
I got a negative, thanks.
So did you do, yeah.
Oh, I did that, it's not bad.
All right, so now let's put it all together. And so this is really the only formula that you need to know. And by need to know, I mean you don't need to remember anything, but this will help rederive you at all of them. And so let's see what it means by this. So it has, let's first rederive our gas laws. And so if we start with PV equals nRT, so this is now our ideal gas law formula. And if we break it down, we have everything that we know. So let's look here for a second. So pressure is always in ATM, volume is always in liters, N is in moles, R is this gas constant, and T is in Kelvin. And so first of all, this is the only place where the pressure has to be in ATM, your volume has to be in liters, temperature, right, is always in Kelvin, so that is fine. But why this is because of the gas constant that we use. So because we're using 0.0821, that's why we're in ATM liters. And I just want to make a point with that. So if you were to just Google gas constant, you would get all sorts of different units. And that's because it depends what your other unit is. And so later we'll look at different calculations with like joules. And so we would use this R. So notice, right, you could do it in pascals. You have different gas constants, right? PSI, inches of water. So you get the point. So different gas constants with different units. That's why for our purposes, we just stick to ATM liters moles and this 0.0821 gas constant. And so now looking at how to rederive our formulas. So we can rewrite this as just PV over NT equals R, right? And R, again, was just a constant. So it's just our constant. And so I could rewrite this now as P1 V1 over N1 T1 gives me R. And I could also still have that equal to any other set then of P2 V2 equals N2 T2. So now we could just set them equal to each other. And so now we just have P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. And so really this is the other form of what I like to say is the gas law you want to know, or like our combined gas law. But what do you notice? So notice how you get Boyle's law back out. We get all our laws back out. Our P1 V1 equals P2 V2. That's just holding moles and temperature constant. We have our other formulas, right? Our V1 over T1 equals V2 over T2. So same thing. So V1 over N1 equals V2 over N2. So you can, right, get our simple gas laws. But what we can also say is let's just say they change all 4 variables or all 3 variables, right? It doesn't matter. You could still solve them as long as you have, enough information. And sometimes it's given in like another simplified form. So this one kind of rederives it. I think it's your homework actually. I remember. It gives you all of them separately. It's just sometimes, so your homework gives an extra law that we didn't go over. So P1T1 relationship. But again, you can derive it from here. So P1T1 equals P2T2. That's fine. But as long as you can get to there, right, that will always work. You also see other alternate forms. Is sometimes they give you this like P1 V1 over T1 equals P2 V2 over T2, but all that that's doing is that you're holding N constant, or moles, right? So my point in showing you all this is that you only need to remember either PV equals nRT, and then you can get all these relationships back out. Or if this is more comfortable, right, write this somewhere on your notes as P1V1 over N1T1 equals P2V2 over N2T2, and then you can cancel out whatever is constant. So I'll kind of add that as a side note. So any variable held constant just cancels. Right, so that's a hint. So you can start with this formula, your big combined gas law, but then you'll look in the problem, what's held constant, what can you just ignore, and then you'll get back to your simple gas laws. And again, we'll do more practice. You'll see this and feel better. And so now all this is saying, this is kind of the same thing, right? Just kind of rederiving everything out. And as long, whatever we're holding constant, we can find the other variables. So now let's try this one. So calculate the volume occupied by 0.845 moles of nitrogen gas at 1.37 ATM and 315 Kelvin. And so you may need this PV equals nRT with RR as 0.0821, and that's again ATM liters. So that's the unit of that R. This is just the units if you were keeping track of them, ATM liters over Kelvin moles.
So the R is 0.0821.
Yeah. For these ATM liters, Kelvin moles units. Do we have answers for volume? Let's see, do people need more time? Give people a little more time before we reveal. You know, just recognize what you plug in where. So that's our pressure, it's already an ATM, that's fine. Our temperature, moles, don't know volume. So then plug it into here, we didn't have to do any converting. So what do we get for volume?
We have 16.0 liters.
16.0, so I see nods from the crowd. So did everybody get that or on their way, see how to get that? So it's just algebra, so you solve for V, multiply all these up together, divide.
I set it up wrong. I put the volume as the 0.845.
Ah, that happens. Yeah, and you could even write out separately, like some people need to do it like that, like my pressure is this, and you write out all your units, volume, oh, no volume.
But it says volume. Oh, we're calculating volume.
Yeah. See, that's why it's always,
So what?
so yeah, some people like doing this over in the corner so you can like write out all your knowns. You can also do that, you know, going back to the balancing equations and moles, all that's hard is kind of putting together all our knowns, maybe all our molecular weights that we need, so just any information. Cool. All right, so now we have some, I think these are cool, because they kind of put things together for us, but they also make calculations easier. And so what I mean by that is we have what's called STP, and this is just called standard temperature and pressure, or standard conditions. And so anytime you're at STP, this is 1 ATM, your standard temperature is going to be 273 Kelvin, so 0 degrees Celsius. And so this is, again, usually an approximation. Mole, so this is 1 molar amount. And this is what's really, really key here. So notice your volume. So this is your standard molar volume of gas is going to be 22.4 moles at STP, or 22.4 liters at STP. So that's super useful because this is a useful conversion. So gas, then you can have your conversion factor of at STP, right? 1 mole is 22.4 liters. So this is really helpful, this trick, so you don't have to do a bunch of extended math sometimes to solve. And so all this is proving it. And so if you were to do this yourself, so they use a slightly more precise value of the gas constant. And again, referring back to Wikipedia, this is the gas constant, so it keeps going on. We just rounded again to 0.0821. They took it to 0.08206 in this case, but so again, slight differences with rounding, but that's all they did. And you get 22.4 liters for your volume there. And so again, this applies to every gas. Again, this is a little bit of an assumption, so probably in real life they would all vary just a little bit, so it depends on like their density and also what they condense at. But for the most part, we just assume for our purposes that even though all our gases are different, 1 mole is always 22.4 liters. We see that here. So again, super useful. All right, so now let's look at Dalton's law. And so all this is stating is that our pressure is additive. And so this first statement here, so the total pressure of a gas mixture is the sum of the partial pressures. And so let's think about that. Our total air that we're breathing in is 1 atm. So that means that the gases in there have to be less than an atm of pressure, but they all add up to equal 1 atm. And again, we're still assuming our kinetic molecular theory. So we have particles of negligible size, so we don't care about their size and they don't interact. Again, making assumptions. And so all this is saying is our kinetic energy is always going to be the average the same, even though they have different masses. It's still same average kinetic energy. And since your average kinetic energy is the same, then your total pressure of your collisions is the same. And so this is, again, all we're kind of saying is that we have a mixture of gases and we can add them up to get the total pressure. We assume gases behave independently, that they're not going to be reacting and they're not interacting with one another. And so this is just the derivation of that you could pull out your pressure and solve for that. So it's basically related to the number of moles. So that's all that's saying. There's different amounts means different moles of these gases. And so since it's related to the mole amount, you could calculate what's also called your mole fraction. And so all this is saying is we could take our total moles, so our total moles, and take a fraction of whatever compound we're looking at, so moles of A, and then that would be proportional to the total pressure and the pressure of that A. So again, we can find our mole fraction, so that's just the number of moles of your component divided by your total number of moles, and then multiply your mole fraction by your total pressure, gives you back out the pressure of whatever you're interested in. And so we can see how this works with our air. So nitrogen has a 78% composition of air. Find its partial pressure. So we can take our mole fraction, so 0.78 times our total pressure, so 1. So that tells us the pressure of nitrogen is 0.78 atm. And then we could add up all the other components of air. So nitrogen, oxygen, and then a little bit of argon there, at least the top 3 components, so not taking into account CO2 and other minor gases, methane, etc. Let's see, lecture goes till 11. All right, I was thinking maybe let's stop here for the day, and then we can do some practice problems instead. So did everyone grab the homework, gas homework? So let's grab the gas homework, and then we can do some practice. I think I moved the chapter 7 homework back. classes until 11. All right, let's just start. I'm going to send the homework over, but let's just start with number 3 down here. How many moles of ideal gas will occupy a volume at 20 liters at negative 100 degrees Celsius and 0.275 ATM?
When it says moles, does that mean we're using the like Avogadro's type of whatever the word is?
Yeah, probably the Avogadro's law, the PV equals
Yeah.
nRT, or the ideal gas law formula.
So that's Avogadro's number or law?
Well, sorry, this is a formula, the PV equals nRT.
Oh, okay.
So this is probably the formula you'll want. Yeah.
Okay.
Let's see, do we have answers for this one?
I got 0.387 moles.
0.387 moles. So I see a thumbs up. So probably the trickiest part was remembering to convert this to Kelvin. So this would be, what, 173 Kelvin? And I think from there, should have been okay.
What was the answer again?
Consensus, I think, says 0.387. I did not plug it in myself, admittedly, nor did I look at the key.
And what's that measurement? Oh, moles.
Yeah.
For problem number 3, would you, so you multiply both sides till you have one variable on a side? That makes sense?
Yeah, so let's see, let's plug it in. So you set it at 0.275 ATM times your 20
Yeah.
liters equals, so we're trying to solve for N. R is our gas constant, T is 173, and then, yeah, you would just move everything over, so multiply these two and then divide by this and divide by your 173.
Okay.
Okay. I realize I'm not that crazy about these practice problems.
Really?
One day I will make a new sheet, but that day it's not today. All right, let's try this one. So, no, it's a new one because I don't like ours. There's nothing wrong with them. It's just I want to do slightly harder stuff. So let's try this problem. So what volume of oxygen at STP is required to oxidize 8 liters of NO at STP to NO2? So what volume of NO2 is produced at STP? And so let's at least help people. So what's our balanced equation, or even just our regular equation?
2NO plus O2 equals 2NO2.
And then, all right, so that looks good. And so now what do we need to do?
When you do your ratio, figure out your percentages.
Yep, so we,
O2 to NO.
yep, so we need to do some mole ratio. And then convert this to moles or some sort of ratio. So give people a few more minutes with this one.
Wouldn't there be like 4 O2s for the last equation? We have 2 NO2s.
Yeah, so then 2 times 2 is 4, and then 2 times 1 is 2 plus
Oh, I
2.
see.
Yeah,
Okay.
those O2s.
That makes sense, sorry.
And what's our new conversion factor that helps us with all these problems? What do we just learn?
You're talking about your PP equals NRT?
So that helps us, but that STP relationship, that's even
Oh, the 1 ATM, 223 degrees Kelvin, 2242.
0.4 liters.
22.4.
Is 1 mole at STP. And so let's go over how to do it. And so this one kind of gets a little redundant because it's always an STP and it's only asking for volumes of everything at STP. But what was our first step if we want to do it really properly with mole-mole ratios and all that? What do we do?
Figure out how many moles you have of the NO.
Yep, and so we can do that. So set up, we have 8 liters of our NO. Now we can use this. So that's a lot easier. So divided by 22.4 liters gives us 1 mole. And so let's see, if we wanted to compare, so it first asked us for volume of oxygen, and then this is where our ratio is at. So now write conversion factor from equation, and for every 1 mole of oxygen, we need 2 moles of NO. So this, right, gives me moles of NO. So now it cancels. And then it wants it volume, so then you convert it back to liters. Now we can just multiply it by 22.4 liters is 1 mole. Yeah, well, it ends up, yeah. So the ratios, yeah. It's just, it's not always that simple, because usually it's not like gas to gas, it's like gas to magnesium, and you'd be going from moles to grams instead. But yeah, this one works out where you could have just done the ratios.
Gas to gas makes it so you can just ratio it, and where once you start adding in solids and liquids, you have to do grams.
Yeah, and then later, I think next week is when we do solutions, well, there'll be molarity, so then it's a different. But yeah, this one, it seems kind of trivial because it's just like gas to gas. I know, everything gets,
I think it's something way too much.
and so of course, with NO2, you could have already skipped, well, they're in the same mole ratio, so I need the same amount, and so they're going to occupy the same 8 liters, but I'll just go through the conversion not to confuse everybody. So again, same thing, divide, convert it to moles, then compare our mole-mole ratios, and then we could convert back, which again in this case almost feels silly, but it's silly till it's not. Let's try another one. I think this is the 3 variable that I was mentioning, but we did not actually have in our homework problems. All right, so let's look at this scenario. And so we're given, we have an airtight container, and this did not copy. Yeah. So that's a volume of 4.25 times 10 to the 4th liters, an internal pressure of 1 atm, and an internal temperature of 15 degrees Celsius is washed off the deck of a ship and sinks to a depth where the pressure is 175 atm and the temperature is 3 degrees Celsius. So what will the volume of the gas be when the container breaks under the pressure at this depth? are we doing?
Is it bad that the part of me that bothered by this problem is the fact that 175 ATM depth of water I know is way below 3 degrees Celsius?
Yeah, I was kind of wondering, like, that would be pretty cool. You know, I'm teaching oceanography this summer, and now this reminds me. So I just learned that apparently like 10 cargo ships go missing a year, like big cargo ships. Like that's horrifying. That was my face exactly. Like in this modern age, we.
Want to know how bad it is? Look how many small ships off the coast of South America and Central America go missing a year.
I haven't looked.
Have you ever looked at the triangle, the Bermuda Triangle? Like, have you ever seen the maps image when they actually have a clear day there? They've actually had planes that fly, not over it because they actually have electronic interference, but they'll catch video footage and you'll literally see just a reef surrounding it of cargo ships, individual ships where you can see into the ocean. Some of them are so big that they've actually stacked up and you can actually see.
Wow.
They call them ship islands.
That's crazy. Yeah, there's also all those like islands of trash too that you'll find on the internet. All right, so you should have at least maybe made it to this step of setting up your 3 variable problem, which is what I was getting at. And then, right, tricky parts, they gave it to us in Celsius. Everything else is fine. Liters is fine. ATM, that's fine. But we just can't be in Celsius. And this is one of those where you might want to identify, you know, this is your, oops, what your V1 is, P1, T1. See, what did people get for their volume answers?
23.755, not including the right sections.
So volume equals, so I think we need 3 sig figs, looks like from our ATM. So you said 232, right?
Yeah.
Or I guess we should round it 233 maybe. It's in liters. So did everybody get that? Just double check any math and plugging it in, doing the times E times 10 to the fourth properly. So as long as you set it up, that's again always a good step. So getting to this point where you're just plugging it all in properly, that's good. And then just doing your cross multiplication to get there. All right, let me find other problem that I wanted to do. There we go. No, that's actually not what I wanted. Sorry, now I lost the problem I wanted to do. Let's try this one, although this isn't what I wanted. Now I have to re-find the one I wanted. All right, let's try this one. Shouldn't be too bad. So now how many grams of gas are present in 0.1 liters of carbon dioxide at 307 torr and 26 degrees Celsius? And so I'll just remind you, 760 torr is 1 ATM. You might need that. do we have moles yet for this one?
Yeah.
So what do we get for moles at least?
Got 0.00165 moles.
0.00165. So is this what other people got? I'll plug it in. So again, tricky parts is if we want to use PV equals nRT, we had to convert to ATM. So I did that first. And then Kelvin. And so now I can multiply. So pressure times volume. Then divided by my temperature. So 299. Then divided by our gas constant. See, I get that as well. So this was really the probably where you want to be step is can you get to the moles? And then now taking it the next step further. So what's your molecular weight of CO2?
44 grams.
So about 44 grams per mole. And then we just have to multiply that. So 0.00165, again, could be rounding. So moles of CO2 times my mass. So about 0.07 grams. 0.0726. All right, so that problem was just to help you connect our moles and grams, because that's going to keep coming back. And then last problem really quick before we take a 10-minute break and then do our quiz. So this is just showing you Dalton's law in action. And so we're looking at, we have some mixture of nitrogen with CO2, oxygen, and water. And the total pressure is 2.5 atm, and then it tells you that CO2 has a partial pressure of 0.1 atm, O2 is 0.4, and water 0.7, so find nitrogen. So I'll give everyone a minute or so. And so what do we get when we do the math? So is this what other people got as well? So again, you just had to subtract all of these from 2.5 to get you your partial pressure. Again, just demonstrating Dalton's partial pressure law. All right, that's a good place to stop. So take a 10-minute break, and then we'll come back and do our quiz. And then y'all are free. And then again, don't forget to pick up your labs so you can look over them for Wednesday. So almost to the end here. All right, I will stop this stream. So thank you.